just a quick revision, what we have done last time. Okay, we studied about weak law of large numbers, Chernoff inequality, and some exponential properties as well in this example in proving the Chernoff bound basically. Then we saw the probability boosting thing. Then we came to the stochastic process. Markov chain, stochastic itself means random here. Markov chain, in which we saw that it's memoryless basically. The current state will depend on the. Okay, my screen is not visible. Okay,
Yes,
sorry.
your screen is not visible.
Okay, I was thinking that screen is visible. Wait a second. So last time we did about we did these Chernoff bound and all, and the Chernoff inequality, and proved this theorem basically. And then we came to stochastic process, basically random experiments which are conducted. And then what is independent, we know that. Then we came up with the Markov chain, that the current state doesn't depend on the whole history. Basically, it depends on the previous state only. And then I gave you the example how the Markov chain can be useful basically, and this was it. And then we solved the assignment basically. Now coming to so I hope so that you know about the stochastic metrics, transition metrics and all. Are they clear?
Yes, ma'am.
Yes. What is Markov chain is clear.
Yes, ma'am.
And when is the stochastic matrix, that is basically the row sum is equal to 1. Can we say that that is basically the stochastic matrix? The sum of the rows is equal to 1, and homogeneous when it is independent of time, it doesn't depend on time. Basically, that is homogeneous Markov chain. Now coming to an example. Today we will do that page rank algorithm, how it works. It is basically a very famous algorithm which is used by Google as well. We'll cover in this lecture today. So before that, let's go through the example, this drunkard walk in one dimension, which is solved in the class as well. So basically, the starting point, let it be 0. And it will either go here it will only go one step. It will either go left side, either go right hand side with half of probability. The same goes here. If it is at I, it will either go at I minus 1 or it will either go at I plus 1. What is the transition probability of Tij? What can I say? First of all, the starting state. What I mean is that the starting, I'll tell you first thing. I'll write it and then tell me what is the meaning of this. Can you tell me what does it mean? A drunkard is there, a walk is there, either it will go left side or either it will go right side. Only one step. That is why it's called drunkard walk in one dimension only. So we are talking about one step only. What does this mean? Mathematical expression which I have written.
Probability of moving one step from the current position is half, and otherwise it's 0.
Which means if what is the probability of 0 to I? Okay, let us not let us take one step probability that if the difference between them, the two, like 0 and I minus 1, or I minus 1 and I is basically 1. So that is why the probability between them is basically half, otherwise it's 0. Absolutely correct. Now I'll write about the initial distribution. What does it mean?
So it means that with one probability, the starting state is zero.
Yes. So can I say in other words that the starting state will always be 0?
Yes, ma'am.
Yes.
Absolutely correct. So similarly, we can define in multi-dimensional also, or graph way. That will come basically for the page rank algorithm as well. But just giving you an intuition, like suppose 1 to 2, it can be here 1, 2, 4, 5, and 3. And then we can make an adjacency matrix and say from where to where it is basically traveling. Or something like this. So basically, the main concept of Markov chain is it's memoryless. Can you tell me what is memoryless property? What do you mean by memoryless?
So it means that
The
from the present state going to the next state only depends on the present state and not on the past states.
From the present, can I say if I'm going from current state from the next state, it depends on the last previous state, not the other history, or only the present state. If I'm going from I to I minus, like, does it depend on the last state only from where we are going, or it depends on the history as well?
Current state only.
Basically, the current state only, not the whole history. If I'm going to I plus 1, it will depend on only I, not the whole I minus 1, or something like this. So it only depends on I here. That is basically the memory less property. Can you tell me now any distribution which is memory less? Not related to Markov chain. We have discussed about binomial, Bernoulli, and all these distributions. So which distribution is which distribution follows memoryless property? Any idea? Any guess? Come on, let's have a guess only.
ma'am,
This
number of heads.
number of,
Ma'am, number of heads in coin toss.
so which is that distribution? Number of heads. If I
Binomial.
So, number of heads, okay. Suppose I toss the coin for the first time, and I got the head, and then I want to count the number of heads. So, first time I have got head. So, second time, okay, that case I can say, but actually, number of heads. Number of heads is depending on only the last distribution. But in many cases, binomial also not follow the memoryless property. To think about that example, usually geometric distribution or exponential follows the this memoryless property. Maybe I have to think some case where binomial is not following. Any example you can give? Yes. Memoryless property basically is followed by geometric distribution or exponential property, distribution. Number of heads, if I think yes, it depends on only the current one. Wait a second. What is binomial? Let's see. Let's go today. I'm calculating the number of heads, and it is depending upon that only. Okay, let's take it as a homework problem, I can say. Okay, if I say that, let's say, uh, probability of getting more than 2 heads in 4 flips. So what is this? Which distribution it is?
Binomial.
Binomial. So is it memoryless or it is with memory constraint?
So is this binomial or sum of binomial?
Probability of getting more than 2 heads in 4 flips. I flipped it first time. I flipped it second time. I'm not calculating. Okay. And then probability of
So it means that you are taking the sum of two probabilities, the probability of getting 3 heads plus the probability of getting 4 heads, right?
probability of more than 2 heads. Yes, yes, yes.
So
3
this
heads
means,
and
so you have added two distributions, isn't it?
yes, yes, yes. Okay, let's take an homework problem only. I'll also think about the case where binomial doesn't follow. Actually, the rule is that binomial doesn't follow the memoryless property, and geometric and exponential follows that. I was giving the like now only I was thinking some example. Maybe I'll think, and we can discuss in the next class basically about this. But if I say about this, you are saying that this is sum of the binomial, which means that probability of x is greater than 2 is equal to probability of x is equal to 3 plus probability of x is equal to 4. Can I say that?
Yes.
So what is, okay, you are saying that this is another binomial and this is another binomial. Is it so?
Yes.
So this is the sum of binomial. But we can't say that this is also binomial. There are conditions that, okay, this is also binomial, this is also binomial, x is greater than 2 also we can consider it as binomial. Okay, let's think next time. We'll again come to this example, or let's have some other examples where you can give me some examples where binomial we are observing that.
Ma'am, can you justify why geometric distribution is memoryless?
Okay, can you give the example of geometric distribution first? What is geometric distribution? Failure, failure, and then success. Is it that? It is also
Yes.
Bernoulli trials, I can say. This is also Bernoulli trials, that either it will be failure or either it will be success. Either it will be failure or either it will be success in the second event. In the third also, either it will be failure or either it will be success, I can say. Is it so?
Correct.
So now what do you think that my success, it will depend on the, like, what is memoryless? Let's first write. Can you tell me what is this basically? X is greater than S plus T. Given x is greater than s, x is greater than s, and probability of x is greater than s is given, and then I have to calculate the probability of x is greater than s plus t. I'll tell you 1 minute. Suppose now, let us take that you have flipped the coins 3 times and you haven't got hit. So what is the probability that it will take more than 5 flips from the beginning? It will depend on. Okay, maybe I'll come in the next class with these examples, because I was in this. Maybe in the previous classes also, geometric distribution being memoryless we have discussed, but with the full proof and examples. Basically, that it will depend on the last event only, not on the successive history, or on the current event only. Can you give some intuition, you guys? Yes. It is failure, Bernoulli, 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 Bernoulli. Everything is Bernoulli. It is failure, 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 or the success. That is what it is. Now, can you tell me like how it is basically memoryless? Let's discuss here. Let's have an interactive session. You also give the feedback. I'll also try for this.
So to start with, geometric distribution is telling us that how many times we have to toss to get the first success, right?
Yes.
So, so the probability that, let us say, we x is equal to 10, that means we need to toss 10 times. Mm, no, let's say probability of x exactly equal to 10, not greater than 10.
Okay.
So that will depend on whether, so two things can happen. Either we have seen, uh, so let us say head is success. So let us say that if we have not seen any heads in the first 9 tosses, then the probability that x is equal to 10 is nothing but the probability that we get head in the 10th toss. So let us say the probability of heads is p, then so we can write probability x is equal to 10 as two things, conditional things. One is uh, we have not seen any head so far, and the other is we have already seen head, because if we have already seen head, then probability x is equal to 10 will be 0.
Can I say that if you are waiting for something like waiting for the like waiting for some text or bus, that if you are waiting for 3 hours for a reply or for a bus, and
Yes.
you have already waited something like suppose something like you have waited for 2 hours, and now what is the probability that you will wait for 5 hours? This probability of x more than 3. Can I write like this? If I'm waiting for some text or bus for more than 2 hours, that is given. And what is the probability of waiting for 5 hours, more than 5 hours in total, which is equal to probability of waiting more than 3 hours in addition, disregarding this 2 hours?
So are you making some independence assumptions?
Yes, yes. I mean to say like I'm unable to convey actually that the probability you will have to wait for more than 3 hours, and say after waiting for 2 hours, basically if x is greater than 2 hours, it's basically waiting for 3 hours only and forgetting the 2 hours, the initial 2 hours which we have waited already due to memoryless property. Now I have to wait for 3 hours. It doesn't depend how much wait I have already done. I mean to say, I have to wait for 5 hours. I have already waited for 2 hours. Now the main thing is I have to wait for 3 hours. It doesn't matter how much wait I have already done. Now, if I say about 10, I'm tossing the coin 10 times. If the ninth, like ninth is basically tail, it doesn't depend on how many of, it doesn't depend on how long I am basically getting the tail. I want to predict that now what I'll get. Something like this. Are you getting the intuition by this? Basically, if I'm waiting for some text or for some bus, for more for 5 hours, and I said that I have already waited for 2 hours, but now what is the thing, I have to wait for 3 hours. It doesn't depend on how 2 hours I have waited, 4 hours I have waited. Now the main thing is 3 hours I have to wait. Something like this. Are you getting the connect? Or maybe with some more intuition or example, I'll think about it, or maybe in the next lecture we can discuss more. Is there any connect with this?
So I'm not really convinced why geometric distribution is memoryless. So what I understand is if we have, so for example, let us say in the 10th toss, we already know that we have seen a success. So we already have to depend on the past to say that probability that x equal to 10 is 0. Do you understand what I'm saying?
What you are saying is that on the 10th toss, okay, let it be 10th toss now.
Now,
Probability of success.
if we already know that we have seen a success in the past in the first 9 tosses, then the probability that x is equal to 10 is 0, right?
But geometric distribution, if we think about the definition of geometric distribution, we'll continue to do until the success is there. If I have already seen the success, then why I'll go to the 10th toss itself? Then
No,
again,
we are not going. I'm just asking the question that, so what is the formula for P is probability of x equal to 10? So it's the probability of failure to the power 9 times probability of success, right?
yes, yes.
So now we know that we have to fail 9 times. So there is dependence on the past. Am I right?
Yes. So you are saying that if we know that 9 times we are failing, it is dependent on basically there is a memory involved there. Is
Yes,
it?
yes, yes, yes. Whatever has happened in the past directly impacts the probability.
What are the other views? I'm also thinking about this. What are the other people views about this?
Ma'am, I think we have to fail only in ninth toss to get to the 10th toss.
Yes, yes. He's also saying that we have to fail for the nine tosses basically to get into 10th toss. Now he's saying that uh, that it is dependent on the previous tosses, basically how we are saying that it is memoryless.
Ma'am, but we only do the 10th toss, ma'am, if we fail in the previous tosses.
So basically this is the condition that probability of x is equal to 10, and given that we are suppose like these are basically this. Can I say I forget about the initial failures here? I only do the 10th. That is what you are saying, the probability of achieving the first success on 10th toss. Or I can say, suppose I have 10th toss, and suppose first 4 tosses are success. Though it cannot be the case basically. So it doesn't depend whether the previous tosses are success or failure, how many failures are occurred before, or it depends. What are your views? Are they starting fresh? Or are they not starting fresh? I mean that geometric probability of first success after so many trials, it doesn't depend on how many trials have already occurred. The same example I gave, it doesn't depend on how many trials. I am basically focused on this trial only, that it x is equal to 10, whether it's failure or whether it's success. It doesn't depend how many failures or how many successes have been done basically. If I am waiting for the text for the last 2 hours, it doesn't depend that basically how many hours I am waiting. That depends how many hours I have to wait basically. Is there a connect, or still some confusion is there? If confusion is there, we can clear in the next lecture or so. I mean to say that probability of first success of trial doesn't depend how many trials, 9 trials or any other trials I have conducted. It only depends on 10th trial what I'll get. I'll get success or I'll get the failure.
Okay, madam. Somewhat clear.
If you want, then we can go through in the next lecture also. Basically, go through some proof of this memoryless property and some examples as well. Come up with that. So basically, we were in the Markov chain. So Markov chain, we saw that memoryless property is there. What about others? Is it clear?
Yes.
So there are many examples, as last time I gave you, that how in RL also reinforcement learning also Markov chain is how it is useful. And we talked about technical aspects also. Now in DNA also, internet search. This we'll learn basically how in internet search the page ranking theorem. It's basically useful. Now coming to the evolution of Markov chain. Let process be given by column vector mu and matrix n. So basically at t is equal to 0, the probability distribution on S is given by mu basically, which means that this is the initial probability distribution mu, I can say. So I'll write something and then we'll discuss about it. This is basically transition matrix. Can you tell me first of all, what is transition matrix? What is transition matrix? Simple words.
So it's a matrix.
Probability of going from one state to another.
Absolutely correct. Yes. Now, what does it mean P1 transpose is equal to P0 transpose in dot M? It's discussed in the class. Yes. This is just a revision. Okay, let's go through it. And then we'll see how we come up with this. So let's see the right hand side. I want that it should be more understood by you. Before going, how can I write this as this? What is this basically? Let's see. Any idea what I have written? Come on. Can I write like this, and how I can write like this here? This thing, how I can write like this? This is directly written in class and explained, yes.
Yeah, so it's multiplication of the matrix with the column vector.
Yes, yes. So what they're doing is just to give the intuition so that if someone have not get that what is this is just the multiplication only. Suppose I take M, which is the transition matrix from first. These transition matrix means I'm going from first state to first state, first to two, first to third state, likewise. And every state to every other state, what is the probability of going? Before jumping, can someone quickly tell me what is 0.6? What does 0.6 means? So that I can be sure that everyone has understood. What does 0.6 means?
Probability of going from one second state to second, from two states to three.
Yes. So are the sums equal to 1? This sum, this sum, this sum.
Yes.
Is this stochastic matrix? What is stochastic
Yes, ma'am.
matrix? Stochastic matrix is where the rows are equal to, rows are summing up to 1. Yes, absolutely correct. So now, suppose I take now P naught transpose. What does it mean that P naught transpose?
We're just taking the transpose of the column vector.
But what is this 0.4, 0.4, 0.3? What does it mean?
So it's the probability of moving from state 1 to itself, state 1 to state 2, and state 1 to state 3.
Is it? Are you sure that it's like from? Is it? It's like that, but that is the transition matrix, na? From state 1 to state 2, state 1 to.
Ma'am,
Yes.
initial state probabilities.
Yes, initial state distribution of probabilities. What does it mean that what is the probability of starting from 1, from starting from 2, from starting from 3? Am I correct?
Yes, ma'am.
Let us take point 2 so that it should sum to 1. So basically, I should start from state 2, start from state 3. This is the initial probability distribution. So that is what they have written, the initial probability distribution into this M, that is the transition matrix. You got this thing? Everyone got it? Yes. Now what they are doing is P naught I, that is ith, P naught I into Mij. Let us take I is equal to 1. So if we'll multiply P naught with the first one, for suppose let it be J is equal to 1. So first, what will be the answer? That is 0.4 into 0.2 plus 0.4 into 0.1 plus, sorry, plus 0.2 into 0.3. Is it so? Am I correct?
Yes, ma'am.
So what is 0.08, 0.04?
0.18.
Okay. So similarly, if I do for this, the other one, I can get it. I'll not do it. I'll get it. Suppose zero point 0.4 into 0.5 plus zero point 0.4 into 0.6 plus zero point 0.2 into zero point 0.4. Similarly, zero point 0.4 into 0.3, zero point 0.4 into 0.3. Is it fine? So I can get the P1 transpose as something like this. Something I haven't calculated, but something like this. That is what they are trying to say. This is the sum of basically I is equal to 1 to S and P naught I is multiplied by Mij. Now, then I can write it as now. Can you tell me what I have written and how it is related to that P naught transpose into this? How it is equal to this thing? Come on. It's easy. Or I'll say this thing, not this basically. What we have done now. How can I go from here to here? Yes, come on.
Ma'am,
And
it's the jth entry.
hmm,
Ma'am, it's the jth entry of the transition of the matrix. That's why, ma'am, we can state it as going from I to J.
this is I to j. That is what they have written. If x naught is in I, then what is the probability that x1 is equal to j? This is this. And what is the probability of x naught is equal to I? Simple. From I to j, that is what it is written. This is conditional probability. What is the probability x1 is equal to j given x naught is equal to I? Can I say this is same as this?
Yes, ma'am.
And this is this only. Now, how I came up with this?
Ma'am, by conditional probability.
Conditional probability, because I have conditional probability A given B is equal to probability of A intersection B over probability of B. So I have this here, x1 is equal to j, x naught is equal to I, and so x naught is equal to I, and so x1 is equal to j intersection x naught is equal to I. So by conditional probability, I came up with this. So as it is like partitioning basically for sum of all i's basically, so I can directly write it as sum over all i's means this will not change, and through the partitioning I can write it as jth entry of the left hand side. That is what we were trying to say. When I multiply p naught transpose with the m, then I'll get the p1. Is it fine? Should we proceed forward?
Yes, ma'am.
Now, Now, can I write like this because of our lemma 1? I can say, again, I can write like this because, sorry, Pn minus 2 into m for this, and m is basically multiplied by this. And going on, I can write P naught transpose into m power n. Can I write? Because I have said that P1, we have proved that P1 transpose is equal to P naught transpose into M. So which means that Pn transpose is equal to Pn minus 1 transpose into M, or Pn minus 1, I can write it as Pn minus 1 minus 2 transpose into M and multiply by M by this. And going on, I will say that M is basically multiplied n times multiplied by P naught. The last will be this will be the last step. So how does it end? How does this evolution end? Basically, the limit thing. Does the limit exist or does it not exist? Basically, let's come to the stationary distribution. Any doubts up till now? Should we proceed? So what do you think? What do you mean by stationary distribution? Come on. Yes, any idea?
So a distribution for which the limit will exist.
Yes, I can say limit will exist, or can I say
After certain value of n, the transition is same.
yes, after certain time.
The matrix is constant. Constant is not changing anymore.
Basically, we'll end up in a distribution which will not change further. Can I say right like this? That is a
Yes.
static stationary distribution that after a certain, if I'm going from Markov chain this to this to this, if I'll follow some path basically, so there will be a distribution that probability of getting to this or probability of getting here to here, it will follow a same distribution. It will not change. The probability values will not change. Can I say in other words? And as the other person said that limit is existing, we'll have that. Can I say? Now, what about this? Though there is some confusion in this in ergodicity that we'll discuss later. What about this? Does limit exist? If I say m square is equal to why and why not?
So it is alternating.
So basically it's periodic, I can say. It's alternating, m going to I identity, then again m, then again identity. So that is why limit doesn't exist. We have a think some property it is called basically if it's oscillating or it's periodic, then limit doesn't exist. Now coming to regular Markov chain. We'll discuss.
M cube is also n.
Yes.
M cube is also n.
M cube is also okay. Sorry. Sorry. So we'll maybe I'll come up with today's lecture. I didn't get that time for coming up with the problems and all. In the next lecture, there is a book called Complex Networks as well, where you'll get that page rank algorithm and all. Or I'll come up with in the next lecture with the stationary distribution examples and ergodicity examples and page rank algorithm that we'll solve basically. This is just a theory which I'm telling you. Next lecture, definitely I'll come up with that due to some urgent issues. I didn't get that much time here. So what is the regular Markov chain?
Ma'am,
Any
who is the author of the book you have referred?
wait a second, I'll check. Maybe you can check any complex network. This is by which I am heading. Maybe this is the same book or not. Though in complex network, any book you can find this, but one of the book is by B.S. Manoj, Complex Network and Networking and Signal Processing Perspective. There you can get maybe page rank algorithm and all. That is basically about networks, complex networks. That is not computer networks. Basically, it's like how the small world networks, or I can say the page rank also comes in the network only, like where to go, which web page is more important, which web page is lesser important. Maybe this or something else. Maybe, in the next lecture, I'll tell you the author of the book, and maybe I'll show you the example as well from the book itself. Is it fine?
Yes, ma'am. One more request. So the link to the previous problem solving sessions we don't have.
Okay,
Can you update it in the website?
okay. So you are getting this sheet, Google Sheet, in which links of maybe I haven't uploaded yet. I'll upload after this lecture, the last lecture. So till lecture 4, are the links available?
Uh, I have seen only lecture 1 link.
Okay. Then I'll update in the all the lectures. Though till lecture 4, it's available in the YouTube channel,
Okay.
Prableen Kukreja, by this name. Though I'll update the links of the sheet as well. Till lecture 4, I have uploaded the videos. Though I haven't. And what about the other TA? He has updated the links.
No, madam. In fact, the link that is there is taking us to another course, reinforcement learning.
Okay, for my lecture 1.
Yes. So there is some problem in the NPTEL
Okay.
website.
Okay. I'll check today. And you can go through this Prableen Kukreja channel, and you can find the playlist of probability for computer science.
Okay, madam. And also the other TA has not updated, I think.
I'll also inform him to update on the sheet itself. Now only I'll update it after this class ends.
Okay, thank you.
So we discussed about the stationary distribution. Now can we discuss about regular Markov chain? What do you think? What is a regular Markov chain?
Ma'am,
Can
a chain is regular if there exists a time after which all the entries of the transition matrix are positive.
Yes, basically all entries, I can say after some time, the all entries, MP has all entries greater than 0, or I can say, so what does it mean that all entries are okay? You said that. I'll write it, whatever you said. Then we'll go through the intuition of that. What does it mean? Okay, all entries are greater than 0. What does it actually mean? Greater than 0, like what does it actually mean?
Ma'am, every transition is allowed.
So basically from every state I can go to the other state, I can say to the other state, every transition is allowed. There is no 0. There is nothing like I can't go from one state to another state. Is it like that?
Yes, ma'am.
Now, suppose it was written something like, though I haven't gone through it much. averaging rows of M. Let's not go in that detail about this. Let's try to understand this only. So how does I got this M square first of all? And what is this empty I star dot M? If you want to relate with this, suppose T is equal to 2, I is equal to 1. What does it mean? And one more thing, can I say regular Markov chain is basically it has unique stationary distribution or it doesn't have? What do you guys think about that? Yes, come on. Basically, it has unique stationary distribution. If I say about this thing, MT, that is M2 I star, let us take it as 1 first row multiplied by M. If I multiplied by this, suppose 1, 2, 3. So if I'm saying first to first, that is 0.1. And 0.16. Suppose then okay, I'm saying the first to second, that is 0.68. And then what is 2 to 1? Again coming to 1, that is 0.1. So 0.68 multiplied by 0.1. Basically, if I want to come from 1 to 1, from that is basically my other M3 that I'll get, which means 1 to 2. If I want to go from 1 to 2 and then 2 to 1, I'll get 0.68 into 0.1. Is it correct? What do you get? I think no one got in the class. Anyone can explain what I have said? Yes, come on.
Ma'am, can you repeat?
What I'm saying is, if I want to say what is from, I shouldn't say like this. First, for 1 to 1, I want to get 1 to 1 maybe. No, it's not like that. It's like this multiplied by this, which I'll get it as what does it mean? MTI multiplied by M. This is what I'm asking you. Let 2T is equal to 2, then I is equal to 1, which means first row of M, this matrix multiplied by M. What does it mean? One to two, that is 0.68. 2 to 1 is basically 0.1. If I say 1 to 3, it is 0.61. And 3 to 1, again, it is 0.3. Like 1 to 2 is 0.68. And 2 to 1 is basically in that 0.1. And 1 to 3 here is basically 0.16. And 3 to 1 here is 0.3. Basically multiplying in this, getting, and then basically getting the average rows of M. Okay. I want you to solve this. Basically, take an example. Like I have taken an example, m and m square. In the next lecture, I want how I got this average rows of m from m and m square. Please note down this. Some hint I have given you. Just note down and say, tell me what is basically this term. Like last time, you have shared the screen and explained it. Similarly, this time also I'll expect this thing. Write this example m square or m cube, and then tell me what is this empty I star multiplied by m. You can take the screenshot or photo. Should we proceed forward? Some hint I have given you, just multiplying by this, then average out. Should we proceed forward? Yes.
Ma'am, so what's the point of doing all this?
It's just a property which I'm telling, like what is the physical interpretation we get, nothing more. Like what is this basically, empty star I star into m, nothing more. Nothing like it's used in any, it's an intermediate or something, just a property which is used, that it is basically just telling like this is equal to the physical interpret, what does it actually, physical interpretation, like to go more into depth of this, how it is happening, this is how it is average rows of m basically. Should I expect like with this example or something, with your example m or m square, I can expect what does it mean? Just this, nothing else, like it's useful anywhere or something. How it is basically like this. Should we proceed forward?
Ma'am, it is like averaging. It's not exactly averaging terms, right?
It is like averaging. But how it is like averaging, that is what, not actual average I'm asking. Yes, yes, you are correct. How it is like averaging, can you tell me? With the example I am asking,
We are
like,
going,
hmm?
ma'am, we are going from one state and trying all the possible transitions. That's why, ma'am, we are including all the transition from ma'am, ith to the nth, ma'am, transition. That's why, ma'am, it is like averaging the terms. I mean probabilities. Sorry.
Okay, if I'm going to m cube, then how can you say like it's averaging of this one? How empty I star? I'm just asking like how, what does it mean? Empty I star dot m, basically it's how it, like what does it actually mean? What is the intuition behind it? Just simply this. I want you should show mathematically by the matrices next time. Like I was trying to tell you, like how it is happening. Nothing else, nothing rocket science or something. Is it fine? Should we move forward?
Yes, ma'am. Okay.
Coming to can you tell me this theorem before me proceeding? Then we'll directly go to the basically the page ranking algorithm. Just we'll have the intuition behind this.
Ma'am, it gives us the limit for the transition matrix.
Basically, it gives us the limit, or I'll write it. And is it for regular Markov chain?
Yes, ma'am.
M transition matrix. This is the column vector, and W has some probability distribution. This is the column vector here, and W is basically the stationary distribution. Suppose for my initial distribution, as it is given that Mn is equal to I'll write and then we'll explain. How, okay, this was fine that Mn is equal to 1. This is basically given to us that if I'm having the transit, can you explain the whole thing first of all before me explaining so that I can know how well you have understand how we got this W transpose here as well. Come on, let's try. This is basically related to eigenvectors and all. I'm not going. Maybe when we'll discuss the problems in the next class about this in detail, then we can go. Today I'm just giving you the intention of everything. Yes, come on. Have I written correctly? Have you understood or the doubts are there? And in which part?
Ma'am, can you explain the second part?
This one.
Yes, ma'am.
So basically, we got this Mn basically from this. Is it fine? Now, mu is this something 1 I'll have here, which means mu 1 into 1 plus mu 2 into 1 and so on till mu n into 1, which is equal to the initial distribution mu 1, mu naught, mu 1, mu 2 till mu n, which is equal to 1, I can say. Is it fine?
Yes, ma'am.
And when we'll do this, this is equal, sorry, mu transpose into 1, this column vector 1 is basically equal to 1, so I'll get with W transpose. Is it fine? Basically, the largest eigenvalue is equal to 1 and all. This we'll discuss in the next class how we are basically, then this is just the intuition I'm giving. I'll go through thoroughly through these all of this basically by the example here, by the page rank example. Next class mainly we'll focus on the questions, stationary Markov chain questions and page rank. I'll come up with the huge example and then we'll try to solve it. Now coming to page rank algorithm, I just want to jump here so that it shouldn't be left. So can you tell me first of all what is PageRank algorithm? It's a very important algorithm for the computer science as well. Used in networks, like I told you, in complex network, in any book you can find it. But what do you mean by that? How was it invented? Why was it invented? Any idea? What does the name suggest? Let us first try to find out the intention behind it. Yes. Why was it invented and what was the main reason for inventing this? Can I say to rank the web pages? Yes, yes. Come on, someone was speaking. Can I say to rank the web page? Yes.
Ma'am, to rate the web pages based on the traffic they are getting.
Yes, basically to rank or rate the web pages, how much important each web page is. And it was basically invented by the Google, first algorithm which was used by Google search engine. So that which web page should be at first and how in the search results. So this is the main important algorithm which is used by Google search engine. So that which web page is important and which should come earlier when we are searching in that search engine and which should come below them. That is the algorithm which is used. So if we want to rank a page on the internet, our first criteria is basically, what does we a layman say that, okay, if someone is not into this, or if we are also studying the page rank algorithm for the first time, what will be our intuition? The more the web pages we are what will one think that, okay, whichever site is visited, whichever web page is visited more often, that will come above in the searches when we search in the Google search engine or any other search engine, Firefox or something. Whichever web page, whichever web page is searched more will come above. Is it that, or some other intuition you are carrying? Like, what do you think?
Yes,
Yes,
ma'am.
come. So basically, can you explain the line which I have written here? More links to web page X means higher rank of X. What does these links mean? Come on.
Ma'am, web pages are linked to one another by hyperlinks, and ma'am, this can lead to increase in traffic.
Are they inlinks or outlinks? And what is the difference?
Ma'am, in links, ma'am,
Inlinks, yes, yes. So basically, how many, yes, you are correct, hyperlinks and all. How many of the web pages, or how many of links are connected to a web page X? That is basically how many of them are connected to X, basically. That is basically the rank. And more are the pages which are connected to X, which means X will have the higher rank. That is basically everyone will think that, okay, more we are visiting the web page, that will go up basically in our Google search engine. That is because it is having the higher rank. Now, uh, example which was given in the class as well. I'll share the same example now. We'll go to the more complex one in the next classes. So which one will have the highest rank and which one will have the lowest rank? Come
3 is
on.
having the highest rank.
Why 3 is having highest rank?
Ma'am, the in degree and out degree both are two. Ma'am, this is
Okay.
greater than
Huh.
anything else.
So basically, mainly we are saying that it will depend on in degree. Right now, we are saying that mainly it is dependent on in degree. So in degree basically is 2. And which one is the lowest rank?
Ma'am, 5.
Okay. And what about 0? Are they at the same
Yes,
rank?
ma'am.
Are they
Yes, ma'am,
0?
5 and 0 both.
Both, because both the in degrees are, though there is an out degree, but it doesn't depend. Main thing is that in degree of 0 is same as in degree of 5. No one is referring to that page. No one is outlinked to 0 or 5. So basically 0 and 5 are not equally not important, I can say. So this was a strategy one. I'll write mathematically, then tell me what I have written here. What does it mean? Yes, what does it mean mathematically? I have written.
Ma'am, for every edge, ma'am, increase the rank by 1.
For every edge,
Ma'am,
can
increase the rank by 1.
For every edge, is it that for every edge we'll increase the rank by one, or is it like in degree, out degree? Is it involved, or then
Yes,
if
ma'am,
you're
in degree.
in degree, how in degree is it visible in this formula?
Yes, ma'am, from J to I, ma'am, it's order pair.
Yes, yes. So if J to I and then rank of ith node, basically it will be increased to 1 basically. What is the limitation in this? In this example, we are like, or in this strategy, mapping to the example, what do you think is the limitation here?
Ma'am, we are not giving the importance which website is linking, and we are only saying
Okay,
that
we are not,
it is
yes, you are
linking.
correct. We are not giving the importance basically. And so what do you think in this example? How can you relate your statement that we are not giving in, the importance? Can I
Ma'am,
say two
zero is
link? Ah, yes,
less
yes.
important. Ma'am, zero is less important than two. Ma'am, we are counting it in degree in three.
So when we are counting it the in degree, for the three, we are counting the rank. We are saying that rank is 2. Can I say by this strategy, the rank is 2? But we are saying that it shouldn't be that when it is coming from 0 or whether it is coming from 2, the rank should be equal. Why it shouldn't be equal? Because maybe 2 is more important. Why 2 is more important?
Its rank is higher than two. I mean zero.
Yes. So basically, we are. Can I say in other words that we are seeing the in degrees of the no like suppose third three is basically 0 is basically connected to 3 and 2 is basically connected to 3. We are seeing the in degree of 2 and 0 as well. In that case, the quality of 0 and 2 as well. Why we are worried about that? Can you tell me? In normal world, why we should be worried about that? If someone is connected, why can't we count it? Why to see the quality? Think about let us think about the Google search engine and think like why if someone is connecting more to a web page, let us give that ranking. Why to be worried about what is the quality or not? What do you think? Can it be some type of fraud or something? Let us think intuitively. Can it be like I want to make my web page at the first page only, like I want to make the web page on the first page itself. So I make the hyperlinks of I made many web pages, suppose, and suppose I have this web page X. I want that it should be coming in first 2 3 searches. For making it to first 2 3 searches, what should I do? I should increase the rank. How should I increase the rank? I will increase its in degree. So for that, I make multiple web pages and I basically link it to this. So can I say that by making multiple web pages, my X web page will come in higher in the rank? Are you getting the intuition?
Yes, ma'am.
So can you now elaborate why we need to see the quality? Yes, come on. Why we need to see the
Avoid
quality?
these
Yes, yes.
frauds.
Fraud.
To avoid these kind of frauds.
Because anyone can make the web page above by creating many web pages and obviously this is tough by making this web page also important, this web page also important, this web page also important. Then it's like a loop. Basically, it's difficult because now what they're saying, so that this fraud shouldn't happen, we should determine the quality of this as well. then only it will be important, not by like making this. So that is what is the main intuition behind that. The other thing is, so what can we do the add the improvements here? If J links to many, first thing is this. I'll come to this also. Second thing which we're discussing is, second part, okay, if J is less important, then give less weight to that. I basically. What do you mean by first? Yes, come on. Can you tell me?
Ma'am, if J links to many websites, ma'am, then it may be a fraud or something. That's why we should give it less weight.
Maybe not a fraud also, but maybe okay. That thing I can relate to the fraud. If J links to many, then we are basically giving less weight means okay. Maybe I'll think about the intuition like can be related with the fraud or something. Now they are saying that don't give equal weight, but if it is linking, this is linking to some other also, so reduce its weight basically to this. That is what they are saying, that we can make its improvement. Maybe we can glance over this again. We'll take a break. I'll go to washroom and come. 6:25 we'll meet again. Is it fine?
Yes, ma'am.
Am I audible? Hello? Am I audible first of all? Okay, now let's go proceed basically. So as we saw that, okay, about the page rank algorithm, that first we saw, okay, let's take the first criteria. More are the web page links. I can say more are the links to the web page. Then that means that higher should be the rank. But then we saw that, okay, how the quality is also important. For that we saw that there can be some frauds or something. Maybe for the other thing I have to look at, like there can be some frauds or something. If some web page want to come at the top, they'll make some fake web pages, and then create the hyperlinks so that they can have the in degree as well, the in degree of the their web page should be increased. So that is why we saw that how the quality is important. And we also saw that if this is linked to someone, it is basically that the less weight should be given to them if it is linking to many of them. Maybe in this also we can relate to frauds or something. So which means that in the strategy too, we should come up with something like the quality should matter. I can say, am I audible on the first place?
Yes, ma'am.
Okay. So I can say that for the strategy too, that it should be like quality should matter. So what does it mean? MJ, I'll first write, and then we'll discuss about what is written. So now can you tell me what I have written and how I have basically improved the strategy 1 to strategy 2, and what is the difference between them, and what is this mathematical formulation? Yes, come on, let's try. Come on.
Ma'am, rank is directly proportional to ma'am, inversely proportional to out degree and directly proportional to the rank of the website it's linking
That
to.
is what we were trying to say, that if it has more uh, the like J is connected to I, so if J has more rank, then it should be more important, I can say. Then it should give more weightage to the rank of I itself. So that is what it is, the rank of J, which means the in degree. And MJ, we also thought, okay, if J, and the other thing was that how many links it is connected to, and this is basically the out degree. Can I say PJ is the in degree here? Can I say PJ is the in degree of J
Yes,
and
ma'am.
MJ is the out degree? Yes. In other words, can I say more are the in degree, more is the rank, more is the in degree of J, more is the rank of I, and more is the out degree of J, lesser is the rank of I? Is it correct to say? Yes. Am I audible? So let's go. Now, the other thing is, could we turn this, like now how to calculate for these many years on? So we saw that random walk there in the first, basically in the starting of the lecture itself, the random walk. Now, to calculate the rank and all, could we turn this into random walk on J and basically make it a Markov chain? That is what we were addressing in the applications of Markov chain as well. Like Markov chain can be used in the internet search, which means in the page rank itself. So say a person starts from random page in G and she moves from page J to page I with probability 1 by mj. Then define the basically Markov chain that should rank the vector p bar as its stationary distribution. Basically, we are starting it and then we are basically moving from J to I with some probability. Basically, now coming to before coming to okay ergodic and all. First, we'll have the strategy. So first thing is it regular? And why if it is not regular?
There may be in website a website that may be not linked to any other website.
Can I say 5? It is isolated. So basically, what about 0? Because of 5, if I don't have 5, can I say again? What are your views about this?
Isolated.
Why isolated? What is the definition of regular Markov chain, and can you map with this and tell like why is it a regular Markov chain now or not?
I'm going to 0 is there's no any edge, man. That's why it's the probability is 0.
Yes. But actually, it should. Yes, that is what. That the probability is 0. Actually, the others should also be like 1, 2, 3, and all. It should also be, but after some time. But this is isolated because we don't have a path to 0. So there can be isolated page which can exist basically. So that is why we can't say that it is always regular. So that is why we come up with some notion that is exploration and exploitation. I'll write in this term. We usually use this term in RL as well. So can you tell me what is exploration, what is exploitation in normal English? English, what do you think? What do you mean by exploration? What do you mean by exploitation? Okay, first I'll write this and then I'll explain this term.
I'm exploring the possible scenarios and work accordingly.
Then what is exploitation? Okay, I'll first write this and then we'll go again to these two terms. First, can you tell me what is what does this mathematical notation mean? Then I'll go again to that. Have you understood it, or I can explain you?
Then staying is allowed in this case. That's why we have two scenarios
To
here.
be stray.
Direct jumping from one website to another. If even though ads doesn't exist.
Yes, yes. Basically, what do we do usually? We can basically, that is what it is called, exploration and exploitation. This is basically straying. If we have an edge, if we don't have edge, obviously we have to do we'll do this. Or if what we are doing is, suppose I have this network, I'll say, or and suppose this. I'm going from here to here, here to here, here to here. I'll never go to this basically, this network, I'll say, these web pages, I can say. For this I have to sometimes explore and sometimes exploit means I'm going from here, the in link is here, the in link is here, the outlink is here, the outlink is here, the outlink is here. I'm basically in this local network only. But now sometimes I have to jump and explore more. This is exploitation, what we are doing. This is exploitation. And some what we are doing, we are following our strategy too. And sometimes we have to explore. This is basically, if I'll relate with the RL technique, I'll just give you an intuition. We use their multi-arm bandit. There we use this. Basically, we have to have the trade-off. I'll not go in depth between exploration and exploitation. It's like, I'll just give you 2 minutes, I'll take and give you. Suppose I have the hotel and I want to, these restaurants, suppose restaurant 1, restaurant 2, restaurant 3. I want to pick which one is the best restaurant. Just I'm giving you how this exploration and exploitation is used in another places also. So how basically which one is the best restaurant. So what I did is I went to restaurant 1 and the food was not good at that day. Then because maybe the cook was absent and some temporary cook was there. Then I went to restaurant 2 and restaurant 3. I liked the restaurant 2 basically the best. Now I thought, okay, I'll exploit this only. I'll every time go to restaurant 2. Is it correct to go to always a restaurant 2? I found out that restaurant 2 is the best among restaurant 1, restaurant 2, and restaurant 3. Is it okay to go in restaurant 2 every time? Multi-arm bandit means I have to select one arm. One arm means among restaurant 1, restaurant 2, restaurant 3, I'm selecting one arm, which one is the best basically. Basically, it has some other things also in layman language. I'm saying that what is the, like there is some distribution. I'll update that. That is something different. But in layman language, it is like I'm going to restaurant 2. I went to them. Restaurant 1 cook was absent at that day, and then I thought, okay, I don't know that cook is absent. I ate the food. I thought, okay, I went to restaurant 2. I find out from that best from 3 of the restaurants that restaurant 2 is the best. I'll always go in my entire life to restaurant 2, which is near my place. Basically, 3 restaurants are near my place. Is it the right option? What do you think? Yes. Do you got that question, what I'm trying to say? Or I shouldn't touch this thing, basically?
I don't understand that cook is absent or
What does it mean? That some randomness can be induced. I'm going to restaurant 1, restaurant 2, restaurant 3. I find out restaurant 2 is the best, which means I'll always go to restaurant 2. But there can be some external factors also. Maybe the first time I went, the cook was absent, or something was chef is not there. Something is there that because of that restaurant 1 is not making the good food. So that is why we say we are exploiting restaurant 2. We are thinking that we'll always go to restaurant 2, but with some 10% or some 0.09%, it's good to explore the other ones as well. Maybe I'll go and explore other time as well. Then maybe some other cook is there and I can get more better food in restaurant 1 than restaurant 2. This cook is absent. It's just like a random thing which can happen at that day which I went. So that is in RL how we use exploration versus exploitation. That there is a trade-off. I shouldn't mean that this arm is the best, this restaurant is the best. I'll always go to this restaurant. I should explore the others as well. Anyway, I have explored. Again, I should like I shouldn't be exploiting. Like there is some percentage with very minimal percentage. I should explore the other ones as well. So that is what we call it as exploration and exploitation trade-off in RL, or specifically in map techniques. This is the same thing which we are trying to do. I know that this is linked to this, I have to go through this. But there is a probability that some are isolated. I should go to, I should basically jump and explore the other nodes as well. Just I was trying to say where this trade-off is basically used. You got the idea of this, or I can explain it again?
Yes, ma'am, got it.
So basically, this is if coming back to this, what we are trying to do is we are trying to say that okay, that I should basically also go to the I'll never go to the isolated nodes if I am following this only, because this is basically they are going to the in degree and out degree and everything. I'll never, the out degree here of any of the node is not connected to this, so I should go to the isolated nodes as well. For that, I should also explore with some minimal probability. That is what it is meant by this. Now coming to ergodic Markov chain. Can you tell me what is ergodic Markov chain? Usually, I also have one doubt in this. Maybe I have to also check how. It's a weaker notion, but there are two properties of ergodic Markov chain. One is irreducible, and the other is aperiodic, which means there should be a path from from one state to the another state. Aperiodic means that periodicity shouldn't be there. If I say, and one statement is given that every regular Markov chain is ergodic. Sorry, am I saying the reverse? Every regular Markov chain is ergodic Markov chain, but every ergodic Markov chain is not regular Markov chain. Is it correct statement?
Yes, ma'am.
So if I say about this, is it ergodic Markov chain? I have the path from one.
We need to check it.
Yes, we need to check basically. But if I say, okay, let's not take this example. Maybe we can come it afterwards. But what is my doubt is like in the class, it's written that coming to this. I myself is having the doubt how it is ergodic Markov chain, because ergodic Markov chain usually have the property that it's aperiodic, but it is periodic here. So how we can say that okay, it's not regular because we have zero values, we don't have the positive value. But about so what do you think about this? How it is ergodic? Because ergodicity, they have the property that it should be aperiodic. But in the class, I think it's told that it's like it's ergodic Markov chain. Am I correct?
Yes, ma'am. Ma'am, but it satisfies the definition ma'am provided.
But the definition itself also says that it should be ergodic Markov chain has two properties. It should be reducible and it should be aperiodic. Like you might be thinking the definition is that there should be a path from one to the other. Am I correct?
Ma'am, in the lecture it was told that ma'am, some path should be ma'am, 1 minute type.
Path should be there. So there is a path that is called irreducible. That is this property. But the other property, which is aperiodic, it is not told in the lecture. Maybe I have to go through it. I think so. That every ergodic Markov chain is aperiodic. If I say about this thing, then I have this M, this is I, this is M, and this is periodic, I can say. Then how can I say that it is ergodic Markov chain? This is told in the lecture. There should be a path existing from one state to another state. So I am having a path basically. I'm having a path. But if I say about periodicity, then this property is not followed. Am I correct? Maybe
Yes.
I'm missing something, or because what I know that ergodic Markov chain are aperiodic. Maybe
Ma'am,
I'll.
so,
Hmm.
so we should consider it as periodic or aperiodic.
It is if we say that it is periodic or aperiodic. Periodic means that which means we are coming. This is periodic. This is M. Then I again M. This is I. This is again M. This is I. This is periodic in nature. Isolating, which means it is periodic. And if it is periodic, then how can we say that it is ergodic Markov chain? It shouldn't be ergodic Markov chain actually. Maybe some mistake. I am something um, missing it out or something. Maybe by mistake in lecture. Maybe I'll see in the next lecture and confirm you. And we'll start in the
Ma'am,
next. Yes, yes.
ma'am, if it is wrong in the lectures, then what should we do, ma'am? Ma'am, we should consider it as regular or irregular,
It is irregular. It is.
periodic or aperiodic.
It is. I think it is maybe next lecture I can discuss with you, because what I think it is periodic, and if it is periodic, it cannot be ergodic Markov chain. But in the lecture they have only, I think, discussed about irreducibility. Irreducibility means there should be a path. I agree that there is a path, but talking about this, then I myself is in the confusion, like maybe I am missing something if it's in the lecture. Or you can also look upon this, that how to, like, in the next lecture you can also look what is basically, is it ergodic or it is not ergodic, and the properties of ergodicity, and we can discuss in the next lecture. Something is given in the assignment as well.
Yes, ma'am. Some questions were there.
Okay, so you can also look, but what I think it's not ergodic. Maybe I am missing something. So we can go through in next lecture that something is missed by me, or okay then, and we'll go, and then how to make it, that is by self loops and all, that we'll go through in the next lecture. And I'll also come up with the stationary distribution questions and all, and sorry, ergodic Markov chain more like in the example of the assignments they have given. Similarly, I'll also come with the page rank algorithm, how to solve, like maybe you have got the intuition, some more intuition about it, and some more problem statements about it, so that it should be cleared. Any doubts in today's lecture? How was the lecture?
Eye-opening, I would say.
Yes.
It was very good.
Thank you. Thank you so much. Okay, let's meet in the next class. And if you have, I'll upload the videos. I'll share the link in the sheet. And if you have any doubt, you can mail me as well. We can discuss on the mail as well about this as well. So you guys have my mail ID, or I'll write once again. So, okay, thank you, class.
Okay.